The process of hemostasis has many components and interacting mechanisms that often appear complicated and difficult to grasp. Multiple factors activate each other from different pathways under the control of various enzymatic reactions in a very convoluted manner. However, if looked at from the perspective of what happens at the injury site to specifically stop bleeding, it is in fact quite simple to understand. Only two blood components emerge as necessary: platelets and fibrin. The following animation will highlight the process by which they work together to achieve hemostasis. The endothelial layer in healthy individuals serves to protect against spontaneous accumulation of platelets and fibrin in the vessel wall. In the event of vessel wall injury, bleeding will occur. Hemostatic plug formation is initiated upon exposure of the subendothelium at the injury site. Vasoconstriction in the region of injury results from the release of thromboxane A2, a major enzymatic product of platelet activation which causes vessel wall constriction. Von Willebrand factor is secreted by the endothelial cells and binds to exposed collagen fibers at the wound surface. Platelets then adhere to the wound through their interaction with bound von Willebrand factor. This process constitutes platelet adhesion. Adherent platelets are activated and attract other platelets through a process known as platelet aggregation. Fibrinogen molecules form bridges between adjacent platelets. This forms an aggregate of platelets that occludes the wound and eventually stops bleeding. This unstable primary plug of loosely aggregated platelets must then be consolidated into a more stable plug. This is achieved through the generation of thrombin at the wound site. Free tissue factor released from subendothelial stores and platelets initiates the coagulation cascade with its interaction with activated factor VII. The complex of tissue factor and factor VIIa converts factor X to its active form, factor Xa. Tissue factor VIIa also converts factor IX to its activated form, factor IXA. However, further generation of factor Xa is inhibited by the tissue factor pathway inhibitor. At this point, the amount of factor Xa produced is insufficient to sustain coagulation. Further factor Xa, to allow hemostasis to progress to completion, can now only be generated by the factor IXA pathway. By this stage, though, enough thrombin has been generated by the factor Xa to activate factors VIII and V, which both act as potent catalysts. Factor VIIA increases the capacity of factor IXA to activate factor X to Xa many thousand times. The increased factor Xa produced in this way, along with its own cofactor activated 5A, forms a complex that promotes the efficient conversion of prothrombin to thrombin. It is thrombin that then allows the conversion of fibrinogen to fibrin. While the process of the coagulation cascade as outlined can be confusing and difficult to retain, it is most important to remember the importance of the final result, fibrin, in wound healing. Fibrin is the biological glue that eventually seals the hemostatic plug and ensures hemostasis. As soon as a small amount of thrombin is formed, the clotting process accelerates and provides more and more thrombin into the wound. At high concentrations, this thrombin quickly converts fibrinogen to fibrin on the surface of the platelet aggregate to stabilize the hemostatic plug. Over the course of the subsequent 7 to 12 days, the process of fibrinolysis dissolves the fibrin in the wound as the site of injury heals, and the cell layer in the vessel wall is restored. Some scar formation occurs, and within a few weeks, the wound is completely healed.